Okay, so today we're talking about what makes a collision elastic, not inelastic, elastic. So what does make a collision elastic? An elastic collision, by the definition, the physics definition is you have a collision, its kinetic energy is conserved. Now, remember, what did we learn in an inelastic collision? We learned with an inelastic collision, kinetic energy is not conserved. So with an elastic collision, your kinetic energy is conserved and momentum is conserved. So what we're talking about with an elastic collision is you have two balls coming at each other, they hit each other, or two objects hitting each other and bouncing off. They do not stick together. Inelastic, they stick together. Elastic, they don't. All right, so for a collision between two objects, A and B, the following relationships can be applied. First one is the relative speed between the two objects is equal but opposite the relative speed after the collision. So what does that mean? Not of, between. So it's equal but opposite. The relative speed after the collision. So what is relative speed? What does that mean? Okay. Well, what this means is that the speed that it approaches with is going to be equal to the speed of separation. But this is relative speed, remember that? So what we have is relative speed, remember, would be VA minus VB because they're coming at each other, right? Equal and opposite would then be VB prime minus VA. We just swapped the sign, VA prime. So before versus after. Okay, so what do we mean by that? All right, so what is the relative speed before? Well, relative speed before is you've got 10 going one way and negative 6 going the other way. So basically what you have is 4 meters per second. Well, if you look at this guy, I'm sorry, that is stupid. That is not the case. Excuse me. You have VA, which is 10, VB, which is, well, this would be 10. This would be negative 6 if we wanted to do it that way. So we have 10 minus negative 6, which would be 16 meters per second. Okay, now after separation, notice what we have. We have what? Two objects moving opposite. So now we have 12 minus negative 4. Which would again be 16 meters per second. So they are the same. Now, relative speed. How do we use conservation of momentum and conservation of energy to find equations? What do we know? How could we prove this? So by momentum, we know that the momentum of A initial plus the momentum of B initial has to equal the momentum of A final plus the momentum of B final. Okay? So now let's start plugging things in. We know that this is M sub A, V sub A initial, M sub B, V sub B initial, M sub A, V sub A final, M sub B, V sub B final. Okay, so now let's put our M sub A's together. So we're going to move this to this side and move this to that side. So we get M sub A, V sub A initial minus M sub A, V sub A final. And we get M sub B, V sub B final minus M sub B, V sub B initial. Okay, pull out M sub A and look what you get. V sub A initial minus V sub A final. And pull out M sub B, V sub B final minus V sub B initial. All right, so that's through momentum. Now we got to look at energy. So let's look at energy next to it. So through energy, this would be kinetic energy, correct? That is conserved also. So what do we know? Kinetic energy of A initial plus the kinetic energy of B initial equals the kinetic energy of A final plus the kinetic energy of B final. All right, so this is 1/2 M sub A V sub A initial squared, 1/2 M sub B V sub B initial squared, 1/2 M sub A V sub A final squared, plus, getting over here, 1/2 M sub B V sub B final squared. Going to do the same thing again. Going to get our M sub A's on one side. Going to get our M sub B's on the other side. First thing I'm going to do is get rid of all these 1/2s because they're all the same, aren't they? So now, M sub A, V sub A initial M sub A, V sub A final squared equals M sub B, V sub B final squared minus M sub B, V sub B initial squared. Pull out our M sub A's again. V sub A initial squared minus V sub A final squared. M sub B here times V sub B final minus V sub B initial. I know, lots of math, isn't it? Okay. So this is the difference of two squares, and this is the difference of two squares, isn't it? So let's see. This is M sub A, so this is V sub A initial minus V sub A final times V sub A initial plus V sub A final equals M sub B, V sub B final minus V sub B initial times V sub B final plus V sub B initial. Now we're going to combine these two equations. In other words, we are going to divide one equation by the other. So I am simply going to take this whole thing and divide it by the other, which was what? If you remember, and I guess you can see where this is going. So we are going to divide by M sub A, V sub A initial minus V sub A final equals, and divide this side by M sub B, V sub B final minus V sub B initial. And now look what happens. This goes, that goes, this goes, and that goes. So what is left? V sub A initial plus V sub A final equals V sub B final plus V sub B initial. But you're going, but that's plus. But look how it's written up here. What did we say? We said A minus B and B minus A. So let's get our initials on the same side again. In other words, we're going to move this over here and this over there. So we now have V sub A initial minus V sub B initial equals V sub B final minus V sub A final. And that is exactly what we just had. We've just proven this. It's some pretty hairy math, but we can do it. Walk yourself through it and see. It's just some algebra and some factoring. But that's the proof of why relative speeds are equal going in and coming out of the collision. So it's a way to check yourself and see if you've done the problem correctly. So now let's go back. This formula that we talked about, this relative speed separation thing, is not on your formula sheet. This guy right here, you just need to know if you're talking about a elastic collision, only elastic. So this one is a memorize. Okay? Remember, the primes mean final. All right, so let's only. So here we have an example. After I erase this extraneous mark, here we go. We have an example right here. 1D elastic collision. We have a bumper car of mass 1 is 1,000 kilograms. And so we have M1 and V1 colliding with an M2 and a V2. What's the velocity of each car after the collision? So here's the thing, you don't know either of the final velocities, which means you are probably in most cases going to have to use a system of equations. It means you're going to have to use both K initial equals K final and momentum initial equals momentum final. So let's see what we can do here to solve this problem. So let's start with conservation of momentum. It's usually the easiest. P initial equals P final. So what do we have here? We have M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, so now let's plug in some values. We know this is 1,000 times 12 plus, what is it, 500 times -4. Be careful, guys. Those positive and negatives matter here. This is going in the opposite direction, so it is actually technically negative, isn't it? Equals 1,000 times V1 final plus 500 times V sub 2 final. Okay, primes or finals, either one works. So that's as far as we can go. We've got one equation but two unknowns. So this is where you know you have to have K initial equal K final. All right, so here we go. Oh, but wait a minute. That's going to be ugly and require some doggone use of quadratics. Do you want to do that? Boy, howdy, I tell you what, I don't. So guess what else we can use? We can use our relative speeds being conserved. So what was our relative speeds? This would be V1 minus V sub 2 equals V sub 2 final minus V sub 1 final. That's way easier. So what was the speed of V sub 1? It was 12 minus the speed of V sub 2, which was -4. That's equal to V sub 2 prime minus V sub 1 prime. So 16 equals. So now guess what we can do? We can work out that top up here and get some numbers and see what we get here. So here we go. Let's work this out. So let's take this and bring it down here, and then we'll have a system of equations. So here we go. 1,000 times 12 is 12,000, minus 500 times 4 is minus 2,000, equals 1,000 v1 prime plus 500 v sub 2 prime. So this is 10,000 is equal to 1,000 v sub 1 prime plus 500 v sub 2 prime. Now, what's really cool is I can go ahead and divide this through by 500. So I'm going to divide everything through by 500 to make it smaller. So now we've got this is 20, this is 2, and this is just 1. So guess what? Now we've got a system of equations. So what is my system of equations? I want them to go the same direction here. So I'm going to do 2v sub 1 prime plus v sub 2 prime equals 20. And then I'm going to do negative v sub 1 prime plus v sub 2 prime equals 16. Now I'm going to use just algebra techniques, and I'm going to change my signs on the second one. So now I'm going to make this positive, this negative, and this negative, because now look what happens when I add them. In other words, I just multiplied through by negative 1. This is going to go away, and I'm going to get what? 3v sub 1 prime equals 4. Divide by 3, and you get v sub 1 final is 4/3, which would be approximately 1.33 meters per second. So v sub 1 is still going forward, even after the collision. Okay? So now we can plug back into either one of those two equations and figure out what v sub 2 is. So now I'm going to take this first equation over here. I'm going to take this guy and plug in. Okay? So 16 equals v sub 2 prime minus 1.33. So I'm going to get v sub 2 prime equals what? 17.33 meters per second. And it's also going to be going forward. I want you to think about that. Does that make sense? You've got a really heavy cart that's going to hit a really light cart coming at it. So what's going to end up happening is the whole thing is going to be going in that direction at the end. They're both going to be going this way, aren't they? It really does make sense. The much heavier cart is going to push the other cart in the same direction, but the smaller cart is not big enough or heavy enough to push the other one backwards. So now we have this. So guys, this is kind of almost a little bit of a cheat. Now, I will tell you that this formula that we just talked about, I'm sorry, here. Going. 2D elastic collisions. 2D elastic collisions have to be handled in 2 dimensions. All right. So here we go. Let's look at this. We've got a cue ball coming in and hitting a billiard ball that's stationary. Stationary ball moves off in a path that makes an angle of 60 degrees with the ball's original velocity. Find the speed of the billiard ball after the cue ball, basically afterwards. So this is going to be an angle of 60 degrees with the original here. So what we have to do is we have to deal with this in terms of what? Now they're both the same. These two are both the same mass, aren't they? That's the first thing you need to notice. If you're talking about billiard balls, the mass of the cue ball has to be equal to the mass of the billiard ball. So they're all just there. We're just going to call them all M. So that's the first thing you've got to pay attention to, is what's happening here. So the balls are identical, have the same mass. So what is conservation of energy going to look like? Well, we need to look at this in terms of the x direction and in terms of the y direction. All right, so what's happening here? Here's something you need to know. In terms of an elastic collision, you're going to see something very specific happen here. This right here is always going to be a 90-degree angle, always. So between these two, only if it's elastic, if it's perfectly elastic, then the two trajectories will be at a 90-degree angle for each other. And it only happens if they are identical. So this 90-degree angle happens if they are identical masses and if it is one of the objects was at rest. Okay? And then finally, only if it is perfectly elastic. So now how does that help me? Well, what it does tell me is it tells me my other angle here. It tells me this angle is now 30 degrees. Well, as it turns out, there's a special relationship there. Turns out this right here, this speed, is the same as this right here. Those are the same thing. So what we do is it gives us a shortcut to figure out, in this particular case, what the final velocities of those two are, because what we have is a right triangle. We have a right triangle consisting of the final velocity of the billiard ball, the final velocity of the cue ball, and this is the initial velocity going in. This is the velocity, if we call this v sub a. We can say this is the initial velocity coming in right here. Okay? So now, what do we know? Well, which is which? Turns out this guy, we got to know which angle is which angle, isn't it? So the ball, the 8-ball, or that 8-ball right there, the billiard ball moved off at a 60-degree angle above the horizontal. So if this were 60 right here, that means that this angle right here between the ball and that is going to be 30, isn't it? It's going to swap those angles. And this is going to be 60 degrees. So what we know is v sub b, this is 15. So it's a really easy fix to find these. What we're going to find is that v sub b is simply going to be what? If we use this 60-degree angle, it is going to be opposite. This is our hypotenuse. So we can simply do 15 sine 60 degrees. Okay? And for v sub c, the cue ball final, we're going to do 15 cosine 60 degrees. So let's look at those. So about 13. And the cue ball would then be going about 7.5 meters per second. All right? Let's wrap up what we know here. So if we have a two-dimensional collision, problem solving. What do we know here? First thing is we need to draw a picture so we can conceptualize what it's doing. See what it's doing, draw a picture, and set up a coordinate system. Right? All right, then we need to categorize it. Is it inelastic? Is it elastic? Is it perfectly inelastic? And what does that mean to energy, etc.? Then we want to break it into X and Y coordinates, right? Components. Is it an isolated system? Most of the cases when we find these things, they're isolated systems. So we know the change in momentum is going to be 0, right? The initial momentum is going to equal the final momentum. So if it's isolated, the change in momentum is going to be 0. All right, it might not be 0 in one direction, but it should equal out. Okay. Then we need to solve. Solve our system of equations. And does the answer make sense? All right, so one last example I want to do for you is what happens if we have a spring in the system. Okay, so let's look at an example of a spring system. Here's our system. We have mass 1 here traveling along at 4 meters per second in the I-hat direction. In other words, it's going straight to the right. We've got mass 2, which has a spring attached, which is traveling in the I-hat direction, but it is now going negative 2.5 meters per second in the I-hat direction, okay? Now, what we want to know is, we know afterwards, this is before. So what's going to happen here is you're going to have the springs collide, or the blocks collide, the spring is going to compress. And then what's going to happen? And then it's going to take off again, isn't it? So I want to find the velocity of the two blocks after the collision. Okay? So we're going to have, in the middle of it somewhere, we're going to have M1. This is going to be compressed. And we've got M2 here. Okay? And then what happens? That's really what we want to know, is what happens after that point. Once they've compressed, now what? Well, let's look. What do we know first? We know initial momentum equals final momentum. This is all in the x direction, so it is a one-dimensional collision, isn't it? Okay, so we have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So what can we fill in here? Well, we're not going to fill anything in here yet. We know it's elastic. That we do know. So we've drawn our picture. We've got to categorize, don't we? Well, if they're not going to stick together, because afterwards something's going to happen, and we want to know, do the blocks go this way and this way? Do the blocks both travel in the same direction but at different speeds? We don't know, but we think probably that's what's going to happen, is probably one's going to go one way and one's going to go the other way. So it is elastic. They're not going to stick together. That we do know. So we know it is elastic. So we can apply what? Relative speed. So we can also use our relative speed. So what does that say? That says V1 initial minus V sub 2 initial is equal to V sub 2 final minus V sub 1 final. That's exactly what that means. And that's our relative speed equation. Okay, so now what? Well, we've got two sets of equations. Let's plug some values in maybe. See what we can do. All right. Or better yet, let's move some stuff around and see if we can plug some stuff in. I'm not sure what we can do here, but let's see what we got. All right. Because right now I don't know M sub 1, and I don't know M sub 2, do I? Or do I know it? I don't think I told you what the masses were, but we're going to need to know that, won't we? Here we go. Mass 1 is, let's just say mass 1 is 1.6 kilograms, and mass 2 is 2.10 kilograms. So now we can plug some stuff in. So we know this is 1.6 V sub 1 initial plus 2.1 V sub 2 initial equals 1.6 V sub 1 final plus 2.1 V sub 2 final. Okay, so we have two equations, and oh, wait a minute, we know the initial velocities too, don't we? Oh, excellent. So I can put those in as well. And I can also put them in right, oops, I don't want to erase that, I just want to plug in for it. So V1 initial is 4, and V2 initial is negative 2.5. So we're going to say this is 4 minus negative 2.5 equals V sub 2 final minus V sub 1 final. Oh, so this is 6.25 V sub 2 final minus V sub 1 final. All right, 1.6 times 4 is 6.4 minus 2.1 times 2.5, 5.25.
Good afternoon, Austin High School. We had another great day here at Austin High School. Got a couple of announcements. I'd like to say congratulations to our boys basketball team on the big area win yesterday versus James Clemens. Great job, boys basketball. Also, tomorrow we will have a home wrestling match. It'll be senior night here at Austin High School. We'll come out and support our wrestlers for tomorrow. Again, we we had a great day. Students, please drive slow on Shady Grove and Motor Road adjacent to Austin High School. Again, we had a great day. We'll see everybody here tomorrow.
And
Have a
now,
good day.
and now look, we have two equations with two unknowns. So I need to solve one of these for one of the two unknowns. I'm going to use this one and solve for V. All right, so now I'm going to solve this. V sub 2 final is equal to 6.25 plus V sub 1 final. And we're going to take this and plug it in right there. So 1.15 equals 1.6 V sub 1 final plus 2.1 times 6.25 plus V sub 1 final. We're going to distribute. We're almost there, guys. The math, you just have to grind through sometimes, guys. 1.6 V sub 1 final plus 2.1 times 6.25. Let's see. Is 13.125 plus 2.1 V sub 1 final. Down. I'm going to put those two together. I'm going to subtract this. That's going to go away. So now we have 1.15. So we have negative 11.975 equals 3.7 V sub 1 final. Now all we have to do is divide. V sub 1 final. I'm going to take that and divide it by 3.7. 3.2, about 3.24 is what I'm getting. Okay, so now V sub 2 final is going to be equal to 6.25 plus that negative 3.24, and I should put meters per second here, and that will give me my other one. So if V sub 1 is going backwards, which we suspected it was, 6.25 minus that 3.24 gives me the other one going positive forward by 3.01. And that kind of makes sense. If you think about it, it shows V sub 1 hits the block. So this is V sub 1 final, and it's now going negative 3 point what? What did we say it was? Negative 3.24. And this is going positive 3.01. Well, they're pretty close in size. You've got 1.6 versus 2.1. So you would think that the speeds wouldn't change incredibly once they bounce together. So here we go. So now one's going forward and the other one's going backwards. They're going in opposite directions of where they were because they're close enough in weight, in mass. All right, so that is a yes, that makes sense answer. All right, we're done with this lecture for today. You need to work, next time you'll be working on problem solving with collisions. Just remember some of your basics. Is it one-dimensional? Is it two-dimensional? When is energy conserved? When is it not? When can we use relative speed? When can we not use relative speed? All right, see you next time.